All right, so let me try and give an abbreviated and clearer presentation of the practice problem that we discussed today on the above initial boundary value problem. And part A of this was to solve the above IBVP, and then the second part was to state conditions needed for a continuous and differentiable solution. So I'll just start with solving it. So if you remember, our typical solution is going to be one of the form phi of x minus, and then the thing that you subtract is the wave speed that's out in front of the spatial derivative. So we have something phi of x minus 2t, and applying our initial condition, we get that, well, this means that u of x0 is going to equal phi, and we know that that has to equal f of x. So that is going to give us the solution that emanates from the initial condition here. This is the line x equals 2t. It's sort of our dividing line. And then these are lines x minus 2t is equal to some constant a, which is going to be greater than 0. Okay, and it's greater than 0 because we know that x needs to be greater than 2t. Okay, so that means that x minus 2t would be greater than 0. Okay, over on this side we have x is less than 2t, and that's going to be determined by solutions emanating from the boundary conditions, or in other words, where x minus 2t is equal to some constant a that's less than 0. Okay, so these are the regions of our problem, and let me just say that this is our big important dividing line there. Okay, so u of 0t is equal to e to the minus t squared, and that is going to be equal to phi of minus 2t. Of course, we can rearrange things by saying, well, z is equal to minus 2t, t is equal to minus z over 2. And so that is going to give us that phi of z is equal to e to the minus z squared over 4. Okay, so our solution then is going to be that u is equal to x minus 2t whenever x is greater than 2t, and u is equal to e to the minus x minus 2t squared over 4 whenever x is less than 2t. Okay, so now the second part of this is state conditions. So solution is continuous and differentiable, or we'll just write that as C1 on the domain. And in this case, we have that if we want the limit as x goes to 2t from above, okay, of u, then that is going to be where x minus 2t goes to 0 from above, okay? And so that's going to mean that we have f minus 2t, or the limit as z goes to 0 from above of f of z. Okay. And our other limit in this case is going to be where x goes to 2t from below over u. So we have the limit as x goes to 2t from x minus 2t goes to 0 from below of e minus x minus 2t squared over 4, or just the limit as z goes to 0 from below of e to the minus z squared over 4. Okay, so these two things need to be equal, okay, for the function to just be continuous. Okay, well, what about the limit as x goes to 2t from above of u sub t of xt? Well, that's going to be the limit as z goes to 0 from above of d dt of x minus 2t, where we've taken z to be equal to x minus 2t. Okay. So replacing things like that, we end up with minus 2, the limit as z goes to 0 from above of f prime of z. Okay. And then the limit as x goes to 2t from below of u sub t, x is equal to the limit as z goes to 0 from below of d dt e to the minus z squared over 4. Okay. So this is going to give us the limit as z goes to 0 from above, okay, of 4 multiplied by z divided by 4 e to the minus z squared over 4, which is going to be just equal to 0. Okay, so this implies that we need that the limit as z goes to 0 from above of f prime of z is equal to 0. Okay, last condition, although it's going to give us the same thing in order for our function to be C1, is that we need the limit as x goes to 2t from above of ux to be equal to the limit from below. Okay, so we'll get the limit as z goes to 0 from above of just f prime of z, and the limit as x goes to 2t from below of u sub x is going to be the limit as z goes to 0 from above of just z over 2, okay, minus e to the minus z squared over 4, okay? Because you bring down this argument from the chain rule, but d dx of z, which is equal to d dx of x minus 2t, is just equal to 1, okay? So we don't have that same factor. So in this case, again, this is equal to 0, and it implies that this is equal to 0, okay? So you see here, okay, that in order for things to work out in this case, you need a derivative of your initial condition function should be 0 in this case, okay? So our sort of 4 conditions are that f itself is C1 from 0 to infinity, that the limit as x goes to 0 from above of f of z equals 1, and that the limit as z goes to 0 from above of f prime of z is equal to 0. Okay, so that's our 3 main conditions in this case. And this ensures that we have what's called a classical solution. Okay. Next part of the problem is to look at if we change the PDE to u sub t minus 2ux equals 0, okay, what are the resulting conditions on f of x, okay? In particular for the initial value problem to have a solution, okay? So now u of xt is going to be equal to some unknown function of x plus 2t. And in particular, this tells us that no longer are the characteristics going up and to the right, as was difficult for me to draw in class. The characteristics are going up and to the left, okay? So this point here on the initial boundary gets propagated up and to the left here and hits the boundary right there. So that means that because this is just linear transport, whatever the value of f of x is here, it needs to equal whatever the value of e to the minus t squared is along this region here, okay? So that's graphically what we can say, okay? To work it out just with the solution, let's remember, again, our initial condition tells us that phi of x is equal to f of x. And that means, in general, that u of xt is going to be equal to f of x plus 2t as long as x plus 2t is greater than 0, which works as long as x of t are greater than 0, which is exactly the domain that we have here, okay? Our whole region has x and t are both greater than 0, okay? I mean, except for this sort of special point here on the origin, okay? So what this implies then, okay, is that u of 0t, which is on the boundary now, which we know is equal to e to the minus t squared, that's also got to equal this function evaluated at 0t. So we have that it's equal to f of 2t. So our condition that we get then is that f of 2t needs to equal e to the minus t squared, because this transport essentially just propagates waves from the initial condition right into the boundary. So we need the boundary to agree with our initial condition throughout, in this case. All right, and that is our problem that we worked on today. Hopefully I made it a little bit clearer by fixing some of the bugs and having a tablet pen that writes. Thanks.